Welcome to LabMinutes.com. In this video, we will look at how to configure a site-to-site IPSec VPN using a static virtual tunnel interface or VTI. So some of the benefit of using VTI instead of the traditional crypto map includes the ability to transport both IP unicast and multicast traffic. You can then enable routing protocol end-to-end. On top of that, also some features that are tied to the interface such as NAT, CBAC, and QoS are supported. So basically what you can do with VTI is similar to what you can do on the GRE tunnel, but without the overhead of the extra GRE header. However, here's the caveat. Anything outside IP protocol may not work across the VTI. So MPLS is a good example, and we will see that in this lab later, that in order to run MPLS, you still require GRE. So in our lab setup here, we have two router R1 and R2 that we're going to configure VTI on. And on top of that, we're going to run EIGRP end-to-end to provide reachability between the two sites. Okay, so we start our configuration on the router R1. Before we do that, let me show you that we already have the EIGRP set up on the LAN side of R1 and R2. So we do show IP EIGRP neighbor. You can see R1 peers with switch 1, 2.1. right here, and on the R2 side, show IP EIGRP neighbor. It peers with 128.4, which is also a switch 1, but it runs verb call site on the right hand side. So now we just have to complete the EIGRP in the middle to have the end-to-end reachability. So we'll start the configuration on R1. As always, it's going to be the phase 1 configuration with the crypto ISACamp policy 10. We have encryption AES256 with the authentication. Just do pre-share key. And Delphi Hellman group 5 hash using SHA, and we'll leave the default lifetime. Okay, next we're going to create the ISACamp key using Cisco with the address specify belonging to R2. And that's 222.10. And we're going to add an option no XAuth. Might not be a bad idea to do that for a site-to-site tunnel. We also are going to enable keep alive or dead peer detection with the inner interval of 10 seconds. Try 3 times. Okay, so far phase 1 is pretty much the same compared to the traditional crypto map IPSec tunnel. Next we're going to define the IPSec transform set with ESP AES256 SHA. So we go ESP AES256 ESP SHA HMAC. Okay, so usually with the traditional crypto map here, this is where you would configure the crypto map itself. And the other thing that you might see is so far we have not defined any access list with the crypto access list, because with the VTI you no longer use access list to match your interesting traffic that you want to perform encryption on. Everything's going to be a routing function, as you would see in a sec. So the traffic that you want to pass over the IPSec tunnel, you just need to make sure you have a route pointing out of that tunnel. So instead of doing a crypto map, it's going to be a crypto IPSec profile, and we're going to call site IPSec profile. Okay, with the question mark here, as you can see, there's no match statement, as in like a match address that we used to see with the conventional IPSec configuration. So we're just going to go set. First, we're going to do PFS group 5. We're going to set. We're going to skip reverse route. We're going to do security association with a lifetime of 1024,000 kilobytes and lifetime second in 28,800. Okay, next we'll do set transform set, and that's just the transform set we configured, and that should be it for the profile itself. Next, this is something new with the VTI, so you need to configure a tunnel interface. Give it an IP address 192.168 .0.1. Since it's a point-to-point, all you need is /30, so 2 IPs, so the other side will be at 0.2. Next we do tunnel source, so we tell which source interface or an IP you wanted to use. So the outside interface of R1 is fast01, so I'm going to tell it to source it from source that interface fast01. Next we do tunnel destination, and again, just to look back real quick over back to the IPSec profile, when you do the set command, there's no way for you to set the peer, and that's because with the IPSec profile, it relies on, or the VTI relies on the tunnel destination, and this is where you define your peer IPs. So here, destination is 222.10, which is the IP address of R2. Next, you need to make sure you change the mode to IPsec IPv4, because by default it's a GRE type tunnel. So you need to convert that into a raw IPsec. And the last command you need is the tunnel protection to associate the IPsec profile you created earlier to the tunnel. So where's the IPsec profile? There you go. Okay, so as soon as you do that, you can see the ISACamp came on. And that should be it. So let's take a quick look at our configuration. ISACamp, there you go. Let me bring up a notepad because we're just gonna simply copy that and use it as our template to build the configuration on R2. Here. So for R2, phase 1 will be the same. The peer IP becoming an IP of R1, 111.10. You have to match transform set, nothing you need to change as far as the profile. Keep the same tunnel number. We change IP address 0.2, and again, we update our destination IP for R2 to point to R1. Okay, so we're going to go ahead and copy that. Paste it on R2. ISACamp came on, and the tunnel 1 status has gone to up. So if you do show crypto ISACamp SA, we are in QM idle state, and if you do crypto IPSec SA, we are also having a phase 2 active. So on R1, you can try to ping the R2 tunnel interface, and we have a successful ping. Going back and take a look at show crypto IPSec SA, and we have a 5 encrypt, or endcaps, and 5 decaps. Okay, so you can see the configuration is pretty straightforward, and once you configure one side, you can pretty much copy and with a slight modification paste into the other side without having to worry about the crypto access list and having to reverse the order of the source and destination IP and all that. And the other thing you need to you might notice here is with the crypto IPsec SA output, there's no local or remote subnet. Okay, everything is defined as far as by the routing function. Okay, so from where we are, you can simply create a bunch of static routes pointing out the tunnel 1, and you will be able to push the traffic over the tunnel. But here, we're going to take one step further and complete the routing protocol. So what we have so far as far as the configuration for the routing, we have the EIGRP1 configured that includes the loopback and the LAN interface of R1, and we have a passive default command. So we go ahead and do router EIGRP1. You gotta do no passive on the tunnel 1 and make sure the network command of the tunnel interface. And try to be as specific as we can, so we put 4 zeros. Same thing is needed on R2 side. No passive tunnel 1, network 192.168.0.2. Give it a second, and now we have a EIGRP adjacency across the VTI. Okay, so At this point, if you hop back to the switch 1 on the left-hand side here and do show IP route EIGRP, you can see there's 172.16.128, which is the VLAN 128 coming across the tunnel. However, we don't seem to be seeing VLAN 129, so let's take a look at the closest router. Looks like this one's not seeing it either, so let's see why. Okay, looks like we have a static route that overwrites the EIGRP that we might have from the earlier lab, so let's remove that. And going back to switch 1, and now we're seeing 129 subnet coming across. So from switch 1, if you do ping 172.16.129.1, sourcing from VLAN 32, let's see, we have a successful ping, and now that we have completed that, we have an end-to-end reachability. Okay, so from switch 1, you can also do like a trace route, 129.1. So the first hop is 2.2, which is the LAN interface or R1. 0.2 is the R2 tunnel interface, and 128.4 is the switch 1 VERF site interface. So now if you look at the tunnel interface where we have to, well, we just configure the IP. So if you do not want to, or having to manage separate sets of IPs just for the tunnel interfaces, although it's just /30, what you can do, since it's a point-to-point, instead of specifying a unique IPs to each tunnels that you might have, you can just do tunnel unnumbered and referenced to the one of the interface on the router. So here we're just going to do loopback 0. Also in R2, IP unnumbered loopback 0. So here just basically save yourself a /30 subnet without breaking anything. So neighbor adjacency came back up. If we go back to switch 1 and do that ping again, our ping still succeeding. And if you do trace route again, instead of having a 192.168 IP show up as a second hop, which is the R2 interface IP, since we on R2 we do an unnumbered loopback 0, instead the loopback 0 IP on R2, which is 0.2, show up, or 172.16.0.2 show up in the trace route. Okay, so you can see that works just fine with that. Okay, the next thing we're going to try, as I mentioned earlier in the video, about if you're trying to run anything outside of IP protocol across the VTI, it might not work, and MPLS might be one of them. So here we're just going to go ahead and enable MPLS on router R1, R2, and on the VTI tunnel interface, and we'll see what happens. So give it a router ID using loopback 0, and then on the tunnel 1 interface, do MPLS IP. So you can see enabling MPLS protocol is pretty straightforward. You do it globally as well as the interface where you want the MPLS encapsulation to occur. So same thing on R2 with MPLS IP globally. Give it a router ID, loopback 0, MPLS IP. So give it a second. So the neighbor comes up, the LDP neighbor. Okay, so if you're not familiar with MPLS protocol, LDP is just the protocol the router use to exchange MPLS labels. So here, if we do show MPLS LDP neighbor, we can see the neighbor and all the connected subnets belong to that neighbor. That's just a part of the information that got sent in the LDP messages. Okay, and the source IP is 0.2 because we make it a router IP from a loopback interface. If you show MPLS forwarding, you can all see the MPLS forwarding table as well without the label that's been exchanged. So far it looks like things is working as it should as far as the label exchange. So you can even try from R1 ping, let's say, R2 LAN interface, which is 172.16.128.1. So you can ping that successfully. You can ping a .4, which is the next hop on the switch. That seems to work as well. However, if you go and try to ping, for example, switch 1, go back to our previous test, you can see we do not have end-to-end reachability. Okay, even from R1, if you're trying to ping anything beyond the VLAN 128, so you can ping, trying to ping 129.1, that does not work either. And the reason being, if you look at the forwarding table on R1, so let's say when you're trying to ping 172.16.128 right here, you can see where it said outgoing pop label. Well, pop label means it should not, the packet should not be encapsulated with any kind of MPLS label. So the packet was being sent as is in IP unicast packet. So that's why when you're trying to ping 172.16.128 where there's .1 or .4, so the MPLS label was not prepended, and that's why it was able to, we were able to successfully ping. But when we're trying to ping 129.1, if you see right here, it said outgoing label is supposed to be 19, so as soon as you ping that and packet exit or trying to exit the tunnel interface, so trying to prepend, the route trying to prepend label or MPLS label 19. But since the tunnel itself doesn't support MPLS, the ping doesn't really work. So just to prove that is the case, we're gonna turn the tunnel or change the tunnel back to a GRE. So we go tunnel mode, GRE IP. Well, before we do that, let's shut it down just to make sure. And then tunnel mode, GRE IP. Let me copy that and then do no shut. We do the same thing on R2. Shut. Change it back to GRE and no shut. So we'll give it a few seconds. Alright, looks like EIGRP is up, LDP neighbor is up as well. So if we go back and do show MPLS forwarding, everything looks pretty much the same. Okay, with the VLAN 192 using label 19. But here, if you're trying to ping again, so instead of just use up arrow and ping, you can see right here our ping succeeded. Okay, at the same time, go back to switch 1 and perform that same ping again. You can see now we have end-to-end reachability, and this is because GRE encapsulations support MPLS as far as the transported protocol. Okay, so just keep that in mind. VTI has its own benefit as far as if it's just a simple configuration with the support for unicast and multicast IPs. It should work just fine, but anything other than that, just be a little mindful as far as what you plan to run over that. And also, I don't think I tried to show you the multicast traffic support. Although we know that EIGRP relies on multicast traffic for the adjacency or hello packets. But just to prove that multicast traffic also really work, we can try to ping well-known EIGRP multicast IP, which is 224.0.0.10. You can see we get a bunch of replies. The one we want to see is this one right here, 172.16.0.2, because that belongs to R2, and for sure that came across the tunnel. So the ping must have gone across from R1 to R2 and then came back as a reply. So we know multicast work across the VTI tunnel as well. Okay, so VTI has its place. If you want to save the overhead of the GRE and you just happen to run IP protocol, then VTI should work just fine. Otherwise, GIE might be a way to go. Okay, the other thing with, just to compare VTI with GRE, when you configure VTI, you must use the IPSec profile, so that basically mandates the termination for IPSec. It has to be in the same router as the tunnel interface, but if you go with the GRE tunnel, you can basically separate the crypto or the IPSec termination from the tunnel termination. So you might have a router that runs just the GRE protocol, and in front of that you might have a firewall and another router that does just the conventional IPSec with the crypto map. For whatever reason, the GRE also allows you to do that because it inserts an additional header with the additional sets of the source and destination IP. But like what we just seen here, you can also, if the encryption or IPSec termination just happens to be the same as the GRE termination point, then you can just configure it this way with the IPSec profile without having to define crypto maps. That's it for this video with the configuration of static virtual tunnel interface. Thank you for watching LabMinutes.com. I'll see you guys in the next video.